For our project, we were trying to calculate the acceleration by using the mass of Callie standing on a scale while going up and down in an elevator. And we use this by using Newton's second law, which is an object's acceleration is directly proportional to the force exerted on the object and inversely proportional to its mass.
Oh.
Okay, what the scale reads is your apparent weight, which also equals Fn, but it's not your actual weight. And your apparent weight can change when accelerating upwards, then your Fn grows, and when accelerating downwards, your Fn shrinks. If the elevator is accelerating upwards, then the mass of the person will increase, and when the elevator is deaccelerating, then the person's mass will also decrease because of Newton's second law.
Okay, so this is the data we collected from the experiment when I was standing on the scale without going in the elevator. I was 113 pounds, and then as the elevator accelerated upwards, my weight fluctuated to 126, and on the way down, it dropped to 106. So we're going to do the calculations for our, to find our upward acceleration. So first, we're going to start with making a free body diagram. We know that when the elevator is accelerating upwards, Fn grows, so Fn is going to be greater than the gravity pulling it down. So we'll illustrate that right here. We'll have Fg there. And using Fn and Fg, we're going to find the net force that both of these are creating. So we know that Fn is 126 times 9.8 to change that into newtons, because that was how much Callie's weight fluctuated on the elevator, and then Fg is Callie's original weight times 9.8, and then when you subtract these, your F net equals 127.4 newtons, and your F net is also known as sigma F. So now we know that sigma F equals mass times acceleration, and if you rearrange this equation, you come to sigma F divided by mass equals acceleration. And then all we have to do is just fill in these numbers now, which was 127.4 divided by 113. And then our acceleration is 1.13 meters per second squared. It's a really slow elevator. Next, we're going to calculate the downward acceleration. So we're going to start with making a free body diagram again, just like last time, except this time we know that Fn is going to be less than the force of gravity, because as the acceleration is going downwards, we know that Callie's mass will decrease and Fn will shrink. So on the elevator, Fn is going still upwards, but Fg is greater than Fn, and we can also calculate that by saying Fn is 106 times 9.8. We got those numbers because as the elevator went down, Callie's weight dropped to 106 pounds, and we're changing it into newtons by doing it on 9.8, and then Fg equals 113 pounds times 9.8, because as we already discussed, that's her original weight, just in newtons. And then if you subtract those to get your net force, it comes to negative 68.6 newtons, which is sigma F. And then, just like our last equation, we had sigma F over m equals acceleration, and when you plug those numbers in, that comes to negative 68.6 over 113, and that's going to equal negative 61 meters, 0.61, sorry, meters per second squared.
hypothesis was supported because as the elevator traveled downwards, my weight decreased, and when it went up, my weight increased.